All right, today's topic, lesson 6, is displacement, velocity, acceleration graphs. Now, displacement, another word for displacement is position. Depends on the textbook and teacher that you have, but they mean the same thing, okay? They're a synonym to each other for all the English people out there. All right, what's the goal? I want you to be able to tell me the relationship between displacement, velocity, and acceleration graphs and complete the necessary calculations. So let's take a look at what I want to specifically look at, and then we'll do some examples and run our way through. So what's the relationship here? So let's go with, we're going to make this into a PT graph, and the next one's going to be a VT graph. And from yesterday, you told me that if I have a position time graph and we put some lines on it, so I'm going to put 2 lines on, I'll go right there and right there. We'll make it simple. Okay. If that's my position time graph, you can see that I started, here's my reference point. The x-axis serves as my reference point. I started at the x-axis, I ended at the x-axis, so my overall displacement was 0. So what's the relationship between velocity and time? Yeah, the previous lesson we talked about what we get when we take the slope of a position time graph. And if you recall, slope is equal to, I hear people saying it, velocity. Okay? So if that's the case, I can calculate the velocity from a position time graph. So there's really 2 sections here, section 1 and section 2. That's because the slope changes. So that means I've changed my velocity. So doing some calculations. I'm going to bring the graphs down just a little bit so I can see them. For segment 1, velocity. And I'm going to stick with delta y over delta x. When I'm given a graph, I might as well keep it simple. So my velocity then, or my delta y, sorry, is the height. I'm going to go with the full triangle. So that's 5. And the time is 5. So that means that my resulting velocity was 1 meter per second. Now in section 2, same thing. Velocity is delta y over delta x. Same height, same time frame. And the one difference is, and from grade 9, recall that this is a positive slope. If you're going uphill, the same direction you read, it's positive. If you're going downhill, it's a negative slope. So this is actually negative 1 meter per second. In this case, I am going forward, and negative 1 meter per second, because I'm using that negative, I still say it's forward, or I can rewrite it as 1 meter per second backward. And you can skip to that final step. I have no problem with that. All right. So what does that look like when I go to create my velocity time graph? Well, for the first 5 seconds, all right, and I'm getting that from this particular graph here. For the first 5 seconds, I have the same velocity, and I've calculated it to be 1 meter per second. So when I come over to this graph, I know that on my x-axis here is velocity, which is meters per second. On the other side, it would have been position, and it's in meters. For the first 5 seconds, I was traveling at 1 meter per second the entire time. I then slam the vehicle in reverse. Don't do this with yours. Use your parents or friends. Okay, and now I'm moving backwards at 1 meter per second. So I would have negative 1, a horizontal line at negative 1. And there is my solution. Okay, so that's what it looks like when you move from position time to velocity time. You are doing a calculation of slope for each particular segment. Okay, moving along then. Here I want to do an acceleration time graph. All right, so acceleration, so A, acceleration, that's in meters per second squared. All right, how is your velocity changing? All right, so it's, again, the same process, and I'll put it under here, to determine acceleration, find the slope of a VT graph. Now today it's going to be fairly simple finding that slope. I just want to show you the why. If acceleration is the change in velocity over time, that was the definition we talked about previous. Velocity is a measurement of meters per second. So I'm going to do a unit analysis divided by seconds. Here's the scary part for a lot of people. I have meters per second over seconds, so I'm dividing fractions. So that means I leave the top fraction alone, meters per second. I multiply by the reciprocal, so that'd be s over 1, becomes 1 over s. So I have meters per second squared. So there's my proof that the slope of a VT graph gives me acceleration. Looking at this graph, my current VT graph, what is the slope of these two line segments? So this one's a horizontal line. So hopefully from grade 9 you recall, horizontal lines have a slope of 0, 0. So that means when I go to do my AT graph, I will have a line on the x-axis, and you can cheat above it, okay, just so you can see that line. There we go. There's my resulting AT graph. So the summary is fairly simple here. Position time graph, velocity time graph, acceleration time graph. If I want to go to the right, how do I do that? Well, in each case, it is find the slope. All right, find the slope. That's what we want to do. The big question then, because you can probably see it coming, or some of you can see it coming, is how do we go the other way? And that's the question mark at this point in time. All right, but right now, going from PT to AT, we are just finding the slope. All right, so this is just talks about average velocity for a second. This is always poorly done on the test and similarly on the exam. So I just want to emphasize this. So let's put a star here. And let's say this is a test question. I'm not going to stray. I'm not going to lie to you. It's going to be on the test. This is the one that most people struggle with the most. Okay. I want to calculate the average velocity between the following points. So remember, I guess I should tell you, this is a position time graph. This is a PT graph with position in meters. This is time in seconds. All right, so how do you find velocity from a PT graph? You are finding slope, okay? Slope is so important, and yet in grade 9, you're rolling your eyes thinking you're never going to use this again. So, how do we find the velocity from AC? So the velocity of AC is going to equal change in displacement divided by time. What is the change in displacement from A to C? So I'm going to draw a line connecting A and C because that's the average velocity. That green line that I just drew right here represents our average velocity. We're going to use it to do our calculations, draw the right angle triangle properly. What we find is that it's going to be a negative velocity. We see that the delta y is negative 5. The delta x is 5. So negative 5 over 5 gives us negative 1 meter per second. And again, because I said negative 1, you report everything as forward, and then you can write it as 1 meter per second backwards. Now, if someone wrote 1 meter per second backwards and didn't have the negative in there, it's still full marks because you're interpreting it properly. And that's something that I'm going to have to talk about to you individually to make sure you understand how this forward and backward with positive negatives work. Okay? So there we go. How do you calculate the average velocity from C to D? Well, C to D, I'm going to say D is right there. Same thing. Draw a line in. Determine delta y and delta x. So it looks like I have had this for delta y equals 4, and the time 5, 6, 1, 2, 2.5 seconds. So average velocity from not AC, I want CD, is delta, or you're just changing displacement over time. So 4 divided by 2.5 which gives us about a value of 1.6 meters per second. Now I'm looking at it, it's a positive slope, so that means that I will be moving forward in that time frame. All right. Now velocity of CE, just to finish this off. So I'll pick a different color here for do the red. CE is that distance right there. Now hopefully most people are looking at this thinking, I don't need calculations. The red line's horizontal. I already know the slope of a horizontal line is 0 meters per second. The average velocity from CDE is 0 meters per second. Okay, and that's taken from a position graph. All right, so what I have left is a couple of examples moving from one form to the next. I'm going to do that in the next video so that it's not quite as rushed, and I'll try to do my best to explain it as I go.